yesterday we did non-relativistic perfect fluid dynamics. I didn't go to non-relativistic imperfect fluid dynamics, which is Navier-Stokes equation, which I think you can look up into any textbook. For example, Feynman lectures has for Landau sheets where you can include. Those who are working in this field, area and collision, of course, they have to know this. But even string theories, and if you're working string theory or cosmology or astroparticle physics, then also you need to know this. And other people, of course, those who are not working any of these, they need to know this for cultural reasons. Let's recall the main result that we got yesterday. This was the mass flux density vector. All three are vectors, but this was the often denoted by vector J. So it is this mass flux. This was entropy flux density vector, and this was energy. So we did all this yesterday. Now, what is the local restraint? I defined a local restraint or a co-moving frame. What was that? Fluid is moving. What is the local restraint? Locally it is at there. So you go to a frame, at that point and at that time the fluid is at rest. So here, by definition, the definition of local restraint, velocity in the local restraint is 0. And as a result, what happens here? In the local rest frame, all three will vanish. In particular, the frame in which this vanishes is also the same as frame in which this vanishes. In single frame, both, all three are vanished, but in particular, let's focus only on mass flux density vector and energy flux density vector. So in one frame, both are vanishing, which is a good thing, because otherwise, suppose you have several frames like this, all moving with respect to each other, and suppose in this frame, let me call this A. Suppose this we call this vector B. In general, suppose you have some vectors like this. Suppose A is 0 here. This doesn't happen here, but suppose this happens. that you define such vectors, and in one frame, one of them is 0, other is not 0. In another frame, the first one is not 0, the second one is 0. Now, you can, suppose you choose this frame and make V to be 0. And that means this is our local rest frame. Suppose you choose this to be the frame in which velocity is 0, then in that frame the mass flux density will vanish, but the energy flux density vector will not vanish. And here opposite thing is happening. So we wouldn't know which one is a good choice. If we choose this to be the local rest frame, then even if it is a local rest frame, energy is flowing. If we choose this to be the local rest frame, then the mass is flowing even in the local rest frame. So this doesn't happen here, which is a good thing. But in general, if you go to relativistic, dissipative or imperfect fluid dynamics, this is exactly what happens, and that causes problems. Frame in which mass flux density vector vanishes is also the frame in which the energy flux density vector vanishes. So this good feature it can be shown that this good feature survives in non-relativistic imperfect fluid dynamics and relativistic. I'm going to show the second part of this statement. First one you can look up in the books. Even if you go to dissipative or imperfect non-relativistic fluid dynamics, these vectors remain parallel to each other. Or they all are proportional to, not all, but the first and the second, first and the third. Because in the imperfect case, there is no entropy conservation. But there is, of course, mass conservation and energy conservation. So those two vectors still are proportional to V. If V is 0, both vanish. And so the same thing happens in relativistic perfect. However, imperfect fluid dynamics this does not happen. We will see why this is so. And this is an extremely important point. It causes endless confusion. In other three cases there is no problem, only in this case there is a problem. In other words, in this case, the frame in which this vanishes is not the same as the frame this vanishes. So there are at least two ways you can define your local rest frame. And there are possibly more ways. So that is the reason of ambiguity. ambiguity or there is an arbitrariness in this sense. Arbitrariness in the definition of u mu. So we will see what are those two definitions. So in other words, in which question is in which frame you will set u to be 0 or hydrodynamic for velocity u mu defined as arbitrary time-like vector with unit norm or unit length at each space-time point. That is, this is a requirement. And since it is time-like, we can always find a frame in which the space chord vanishes. Always find a frame in which mu becomes this, and this is the local rest frame. This is the definition of the local rest frame in characteristic fluid dynamics. So in this frame it is this, so in any other frame what will it be? Can you write down in general what is u mu? Just try to make a Lorentz transformation to whatever frame you want to go to. Suppose you want to go to a frame which is moving with velocity v, free velocity v, with respect to this frame. Then in that frame, what will be? It will be gamma 1. And this is also has the same norm. This is also of the norm. Where v is the free velocity. With velocity in LR. So that is a trivial exercise and we'll discuss it in the tutorial. Just one line proof. operator. Symmetric. Now operate this on u mu and see what you get. What do you get? Zero, because of this. What does it mean? This operator is acting on core velocity u mu. U 0 means, suppose if it acts on an arbitrary 4 vector, let's say it acts on some vector A, which has two parts, one which is parallel to u mu. In any vector you can write like this. There's some part which is parallel to u mu and other part which is perpendicular to u mu. And when it acts on this, what is going to happen? The first term will survive or vanish? First term will vanish. And the second term will give? Yeah, so what should I write here? A mu perpendicular. So that will survive because it is orthogonal to mu. So it is projecting out on the three-dimensional space. We are talking, this is a four-dimensional space, and u mu is the 4 vector. And you project onto some space which is orthogonal to u mu, which is the three-dimensional space. Properties of this projection operator, which you should verify. The projection operator, the product of two projection operators is another projection operator. This is 3, and the local restraint is diagonal with these elements. What is the connection between this u mu and a particle velocity, small u mu? Is there any connection? Fluid has, suppose, has some particle which is moving with some velocity, small u mu. Is there any connection with this? There is no connection. This is the bulk fluid velocity, nothing to do with individual particle velocity. We have not still specified completely what is u mu. You just said it is a time-like 4 vector with unit norm. So we have to use precise definition. I have already defined a mu when we were discussing relativistic kinetic theory. So what I am going to do now is I am going to say take out set that this is parallel to this. So and some constant and n mu physically stands for flow of some conserved number like baryon number or charge number, etc. So we are saying that u mu is parallel to the flow of some conserved number. It stands for flow of conserved quantum number. So they are parallel. These two four vectors are parallel. What is n mu u mu? Now let's first do n mu n mu. Is this? So you can write u mu. For n, I can write either of these. I can write as square root of n dot n, right, using this, or I can write dot stands for 4 vector scalar product. So this is an explicit definition of this given in mu. It tells you what is how to construct u mu. What is in mu LRS? Definition of, just look at this, u mu becomes 1 0, so it is n times 1 0. So in general, mu is n gamma 1 . N is n 0th part time part of the n mu in the local Gaussian, and it's also clear that n is a Lorentz scalar. N0 is not a Lorentz scalar. This, okay, clear? Why is N0 not a Lorentz scalar? Varies from frame to frame, of course. While this is Lorentz scalar. To local rest, and there is no free flow of the conserved particle. There is no baryon free flow in the local rest because Ni is 0. You can see that. And this factor is just to ensure that mu is of unit norm. But apart from this, so this is the normalization factor. Apart from the normalization factor, mu and nu are the same. In this way of defining mu. Now, with lambda ellipsis definition of mu. According to lambda ellipsis, it is not the baryon number, but the energy flow. Energy flow vanishes in the local rest. So we can define so this is like an eigenvalue equation, looks like an eigenvalue equation. This is the matrix. This is eigenvector. When it acts on that, you get this as eigenvalue. The same vector. So this is an eigenvalue equation. So once again, note E mu mu. What is this quantity? What is this? Or you can write from here. Just like we did there, I can write this mu as this quantity divided by epsilon. By epsilon, I can use either of these two expressions. I write this symbolically. This T dot U dot P dot U stands for this, and UTU stands for this. So unlike in the Eckhart case, this is not an explicit definition because you're writing u mu and in terms of u mu. It's u mu on the both right hand side as well as left hand side. So this is an implicit definition. Left hand side is a 3 vector, right? And u mu is parallel to that 3 vector. Look at this quantity here. Evaluate this in the local restaurant. Evaluate this local restaurant. Which terms will survive out of 16 terms? Only when mu is 0 and mu is 0 that will survive. So it's T00. So T00 in the local restaurant is which is a Lorentz scalar. Of course, T00 is not. What value of mu will contribute?
0.
Only when it is 0. But mu can be anything.
T mu 0.
So it is T mu 0. Yeah, so what is the value of that? I want to take the value of this. Look at this. T mu nu 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 is only when T0, so it is going to be epsilon u0, which is epsilon 1. Because in local ratio it is 1 0, so epsilon 1 0. Which means that is no. Because epsilon times u mu is the flow of energy, and in the local rate string there is no space part of it. No free flow of energy in the local rate string. So again, this factor is just for normalization. Make sure that u mu is of unit norm. So apart from this factor in the denominator, u mu is parallel to this covector, which is energy flow. Apart from normalization factor, so these are the two most common or most intuitive definitions of Descartes and Dunbar. Two most.
Descartes' definition works for anything conserved in time, I guess, right?
Descartes' definition had an n in the denominator, right?
Right.
U mu was n mu upon n. If n happens to be 0, then this definition cannot be used. So at Rig and LHC, where n is very close to 0, the net baryon number is very close to 0, you cannot use this definition. You have to use lambda distribution. But at larger baryon number density, you can use either of them. Start immunity. It is the immunity for fluid, depends on space-time coordinates. To construct this, we'll proceed the following way. We construct this in the local rest frame. And once you have this in the local rest frame, going to any other frame is straightforward. You can either make Lorentz transformation or you can guess the form, etc. So let's first construct this. So again, remember the definition of P mu in the kinetic theory framework. It was a 4x4 matrix. What was the element here? But what was the meaning of that?
Energy.
Energy, not energy, but energy density. This was energy density. And this was, there are three numbers here. What was the meaning of those three numbers? Not momentum, energy density and energy flow. Energy flow, and here this is momentum density and momentum flow. But of course they have symmetry. So this is energy density or energy flow. This was momentum density. But because this is symmetric, momentum density is same as energy flow. And this was the stress tensor or pressure tensor. We'll use this to construct the menu in the local rest frame. So, this is the energy density. Now, what about energy flow in the local rest frame? Why should it be 0? What is wrong with having energy flow in the rest frame?
is it more project to you?
It's declaration of local residence.
T mu is giving you that. You don't have an answer of what T mu is, right? Like U mu can have an energy flow, but its projection will give you epsilon naught 0.
What was Weinberg's definition of local restraint or perfect fluid? Okay, we are doing all this for perfect fluid, right? We are not yet gone to imperfect fluid. So we are constructing T mu nu for a perfect fluid. This is for, let's say, perfect fluid. What was Weinberg's definition of a perfect fluid?
Moving frame. So you are going into the frame of local frame of the particles.
Yeah, but what is perfect about? What is perfect fluid?
No.
If you go to that frame, what happens?
There is no transfer of heat.
I have not shown anything about it. Weinberg's definition of perfect fluid. I gave two definitions. One was Landau's definition, other was Weinberg's definition. To go to the local rest frame or a co-moving frame, fluid is isotropic. Observer can look in any direction and he finds the same thing. So fluid is isotropic. Now, this is energy flow density actually. So if I integrate this over all volume, what will I get? I will get energy flow from 3 vector after integration over volume. But you can, if this gives some vector, then that means there is no isotropy. It is choosing some direction. So in the isotropy requires that this should vanish. So T0I should vanish due to isotropy. And similarly, if you integrate this over all volume, you will get momentum, total momentum, and 3 vector. That cannot be non-zero because that chooses a direction. This should also be 0. Recall Weinberg's definition. Now what remains is to, we already determined this, only have to determine this part. So this is, as I said, is a space tensor or a pressure tensor. Do you remember Pascal's law in undergraduate physics? If you have fluid or water in a container, what does Pascal's law tell you? Put some surface, imagine some surface in the place. Imagine some surface, pressure is acting perpendicular to it, and it doesn't matter in which direction you are looking at. Any orientation of the plane, pressure is the same. So that is Pascal's law. So that tells you that components along the diagonal, because this is like T0xx, or for Txx, Tyy, or T11, T22, T33, corresponding to x, y, and z direction. They cannot be different because it is isotropic. You can look at it another way. Isotropy implies invariance under rotation. And a matrix which is invariant under rotation, orthogonal transformation, has to be multiple of an identity matrix. Let me write that. any orthogonal transformation, which implies it should be a multiple of an identity matrix. So because of that, these three elements become P, P, and P. And what about the rest of these elements? Off diagonal elements? They should vanish. So T mu nu LRF for perfect fluid. To know if this is a matrix or a tensor with two indices, you know it in one frame, you can find it in any other frame by a lot of information. So I think that can be done in the tutorial. Find P mu nu in any frame. Making Lorentz transformation. But there is a quicker way of doing it, and you can guess look at this okay, epsilon. So from this suggests that it should be like this. Because if you go to local base frame, you can do 0, 0 or T 0, 0, you will get epsilon. And other numbers, because there are these P's, you can write it as delta. Remember, in the local race frame, this operator was -1, -1, -1, 0 and -1. So this suggests this. You can actually verify whether by going to the local race frame, do we get this or not. You do get it, right? Because suppose you get T 0, 0, this will give you epsilon, and what will this give? What was delta 0, 0? In the local restroom it was 0, so this doesn't contribute. You're left with only this. Now let's talk about say T11 in the local restroom. This will not contribute, but this delta 11 is -1, so you get P there. So since these two tensors agree in one frame, they have to agree in all frames. They are identical. This and one frame, namely LRA. They are identical in all. This is correct in all frames.
Sir, delta mu in LRF, that is actually 0, 1, 1, 1.
Yes.
So then
No, it was -1. Only when you had mu here.
Oh, mu, then it is 1, 1.
If one covariant, other contravariant, only then it was +1, otherwise -1. So we got the expression for T mu for a perfect fluid. Okay, now let's go back to these two definitions of U mu. Vikas definition and Lorentz definition. What was Vikas definition? times now what was Landauer's definition? It was mu now we have this is two in general, but now we already know what is T mu nu. So substitute and tell me what you get. Is this satisfied? So that means the energy flow, this is energy flow. This is particle flow, a conserved particle. And both are proportional to u mu. So, if mu is 1, 0, then both of these vanish. Ni or n vector of x ni is 0 is equal to Ti. Ti is 0 or T0 doesn't matter. Which means both of these have no space parts. So whichever definition of u mu you use, if u mu space part is 0, the space part of these two also becomes 0. That is, if ui is 0, then these two are also 0. So there is no ambiguity here about definition of or choosing your local rest frame. If you choose the frame in which Ni is 0, then automatically energy flow is also 0 or vice versa. Now later on, if we go to dissipative fluid or imperfect fluid dynamics and construct T mu nu, then this property is not satisfied. And that causes this ambiguity or arbitrariness. You need two different definitions. Okay, now we can derive fluid dynamics equations. Insert T mu nu. We had already written down non-relativistic fluid dynamic equation, right? Euler's equation, continuity equation, energy balance equation, entropy balance equation. Here also we can write down similarly continuity equation, energy balance, momentum balance, etc. So, and they follow from conservation laws. This is number conservation and this is energy momentum conservation. And using this we'll derive the fluid dynamics or hydrodynamic equations. First, the continuity equation. 0 equals L mu mu. What should I do now? Nu is do this derivation. get one equation and this theta, what this is definition of theta is del mu u mu. It is the four divergence of the velocity, and it tells you how the fluid is expanding or contracting. So this one, theta, is the local expansion rate of the fluid. So theta is positive. Suppose theta is positive, so then let me take it on the other side. If theta is positive, that means expansion rate is positive, then the derivative of n is negative. What does that mean? Fluid is getting diluted because of the expansion rate is positive. Dilution due to expansion. If it is negative, it is the other way around. So that is the physics of this equation. Okay, once again, let's start with energy conservation law, del mu T mu nu equal to 0. We start with this and derive the energy balance equation. So what should I do now? I substitute for T mu nu, which we know. So epsilon du mu okay. Now what will I do now? So tell me what should I do? This del mu is going to act first on this. Let's first act it on this. So what will I get? How many terms will I get? I'll get 3 terms. So there are 3 quantities here. So del mu, and del mu acting on epsilon. This is one term. Then try to do it yourself. It is not difficult. mu acting on P, and then there is G mu. G mu is a constant matrix, so del mu is not going to act on that. And again here I will have three terms. It's similar to the first term, so I can actually look at the first term and the third term. First term was epsilon u mu u nu, and the last term is plus p u mu u nu, the same thing. So I can simply replace wherever there is epsilon, I can write epsilon plus p. So let me replace here. Epsilon plus p. Here. Let's look at these terms one by one. What is u mu and del mu? I had defined it there as capital D. U mu, capital D, acting on epsilon plus P. This is the first term. What about the second term? Epsilon plus P. And this is the expansion rate. Okay. This term
Epsilon speed linear.
is epsilon plus P. T epsilon linear. And the last term. Bring it right. Okay. Fine. I hope it's. Are you taking this algebra? Okay. Now let me project this on. Project this. On u nu. Then pre-multiplied by u nu. So what will the first term do? It just give me d epsilon plus p because u nu is 1. Here this term gives this. What about this term? You are bringing in u nu from the left. I gave you some homework problem today, earlier in the talk. You bring in u nu on the left.
Only del mu only.
You have u nu d u nu, and according to that homework problem, it vanishes. You get u nu, and this is last term. Capital D of P. Now this is getting cancelled. So you get d epsilon. You get d epsilon equals minus epsilon plus d. So again, this is an expansion rate. If it is positive, the energy density will keep on decreasing. If it is negative, energy density will go up. got the continuity equation, and this is energy balance equation. What is conserved?
Entropy.
Entropy is conserved, yeah. That is equivalent to this energy. It can be shown. What about something else is also conserved, right? Total momentum is conserved. So to get that, that is the relativistic Euler equation, which is the momentum balance equation or equation of motion. That is obtained again. We start from the same equation here, but instead of projecting on u nu, we'll project on a direction which is orthogonal to u nu. Okay. So again, once again, I'm going to use this equation here. So this was projection on u nu. Now we take projection on take a projection on space which is orthogonal to u. So you act by this projection operator. Apply this to this equation. Let me practice here. I'm going to apply. So let's look at one by one. What will the first term give? Why will it give 0? Delta mu nu acting on u nu, 0. Projects onto space which is orthogonal, so this gives 0. The first term is 0. Okay, I can write first term is 0. Now acting on this, it will again give 0 because operator will, you can just push up to here. There is not a derivation in it. It's not a derivative of it, just a projection operator. This will also give me 0. Okay, here. Now, you can bring this here and remember the definition of delta mu nu, which was g mu nu minus 2d mu nu. So first this is act by g mu nu. That will only bring this mu, replace it by mu. You get epsilon plus p. G mu nu acting on this gives me d mu. We are actually, no, it is not this, but this. This is our projection operator, which is by definition that. So when I act on G mu nu, I will get mu mu.
But say D has u mu del mu term.
Now I am working only for this, looking only at this. So G mu nu acting on this will give me this. For D and mu. Epsilon plus P remains, and this d u nu will become d mu. Okay.
Next one is 0.
Next term is 0. sandwich between two u nus. This is one u nu, this is another u nu, and there is a d in between, so that is the term. So you get 0. So we have gone up to here. And again, let g mu nu acting on this will give minus d del mu p, right? And now this acting on this will give me mu nu d p, and now this is 0. So what does this mean? Correct? Check. Yeah, so this is what we get, but now let's go back to this D, which was defined as this was the definition of D. So this will be using this definition I get epsilon plus E mu minus u mu T minus u mu another u mu which will be just 1. This u mu and this u mu is going to give me 1, and I get
No, one is you new.
So there is 0
The D has you new del new.
yeah,
You knew till
you have to sum over all the
yeah, it is I'm substituting that here, but I get this. So something can be wrong.
Write the D as you new del new.
So that's a plus, right? I mean, that's plus u mu del dt. The equation is wrong. So the equation is wrong.
Okay, I should,
That's minus and the next one is plus.
this is minus,
The next one is plus.
this is plus,
Yes.
because of this minus.
Yes. And they cancel.
So this is plus.
And now they cancel.
Okay. Is that what we want?
No.
I think we have missed one term somewhere. E epsilon is missing. Because we want D epsilon.
So the dummy they have to cancel. See, he's not using that.
He's using that. See, you had a u mu outside. And you subtracted with the dummy index.
Oh, I see.
That you should not do, right?
Oh, yeah. Yeah. You're right.
Say that.
Okay. That will
But what is wrong? Can you
Does
define
it
that?
write the
So
D
the
as
D
you
can-
new del new?
So
Which
dt
D?
comes in.
So you have contracted
Here?
with a dummy index.
In the small box.
Here? What should I write?
D alpha, u alpha, d alpha.
U alpha. Yeah.
U alpha.
Alright.
Then you can contract
You
with
can't
u.
contract it.
Then, not perfectly right. Let us say that
That sounds looking like delta. So the projection of
this one.
We've not done the homework, but that's
Is that what you say?
Yes.
Great.
now that
And now, when alpha is mu,
That's what.
no, when mu is
That will give me G mu, G mu alpha.
So now we use the homework you've given, the second homework, which is on the projection operator. That u alpha u mu is delta alpha mu plus the projection.
this one.
Yes.
You want to go back to G mu nu and position operator?
Yes, so we give a delta alpha mu and
No, we have to still act by del. We are not acting. This term is same as, this is obtained by acting.
Maybe you can give the final equation and we do it in the tutorial. Lots of ETCs.
With the time. Alright, so final equation, maybe balance or momentum balance equation is act by this to gain this one I have not defined, which is so we have got this and dxr is missing somewhere. So trying. So we got continuity equation, energy balance equation, momentum balance equation. So that is this is the relativistic Euler's equation. No, this is energy balance equation. This is what I wrote some different equation. This is what we will get. Gluon plus G. Did we get that? Gluon plus P, D, mu is gradient of these two together.
That's just writing that thing as del projection operator minus.
Del mu and u mu d together is that operator. So, and I think that nothing is wrong. I was looking at different equation. So this is the relativistic Euler's equation. So it shows that this is an acceleration. And this is the pressure gradient. Because of the pressure gradient, the fluid is accelerating. Now you can, there is a time you can also see what happens in the Gaussian case. We know the velocity in the Gaussian case. It was one of the problems. So straight line. Alright, so I will stop here.